So can you hear me well? And audio video is kind of okay, except the echo. So let me know if it's okay, then plus if there's some problem, let me know. And please get the 8.2 file from the template code and the classroom. Today we'll have really fun topics with a lot of equations and something that actually can solve a lot of problems. And we'll start working with Pytorch. That's great news. So while we're waiting for more people, hopefully more people will join, because this will be really, I think, exciting transition from Numpy to the Python. Yeah, I will wait for a few more people and then we'll start properly, hopefully, if there is somebody joining. And I will also brief you in on the results of the homeworks and the scores for the course from the yesterday. So yesterday evening I marked all of the data that I have. So if there is something new in the scores that is not yet covered, but anyways, so we will check that out as well. Just a quick note for today is that when we will move to the Pytorch, that we will start right at the beginning. From 8.2 template, we will start working with Pytorch. So if you look at how it's historically been, like the TensorFlow was one of the first proper deep learning libraries after Theano and other the ancient ones, and it kind of exploded in early like 2016 till 2018 or something. Like that was the rise of the proper deep learning models, and then Pytorch, because it is so versatile, dynamic function graph and debugging capabilities and everything, so it is dominating the field in the research and also in the production now, because you can export it to Onyx or any other way and then use it in the production. So we will work with the Pytorch the rest of the course. Yeah, so that will be real. So you will see that you can go from like vector math till pre-built C++ compiled functions just in a few lines, and debug function graph in between. So it's not like TensorFlow where it's built. So it's really capable and really powerful framework. So like in ancient days there was MATLAB, then Theano, then like TensorFlow, and now Pytorch is the one that is dominating the field. So that's a brief intro. Just a second. So please, let's start before the results. Make sure that you have 8.2 template ready for work. So I need 8.2 template. So is template code ready for work? Plus minus, if there is some problems, let me know. I see two pluses. Let's wait for a few more pluses and then we'll start. Still 2 pluses, but we have a lot of people. So anyways, also, okay, more pluses coming in. Also, I have the same code available in the Mega, so if somebody is not accessing the classroom, can get it here. Okay, so I see those 4 pluses, and hopefully others also will join. So then let's examine some of the results. So if we see in our score table, Gintz, VeA are the best ones in this course so far. Then Kristaps, both Kristaps are good also. And then there is a large danger zone. So I even did not include those that are even more in danger zone. So I mean, danger zone means that it's possible that you might fail the course if you're not submitting the homeworks. So I also liked some of the results that was like Gintz submitting. There's like adding extra annotations for those robot arms. That was really nice. Also VeA did a really good job. So anyways, in Kristaps not graded the Astrid game. I will double check it. I think yesterday I grade everything that was resubmitted, but I will double check it. Anyways, so I really like if someone makes something like next step, not just what's required, and then I would feature that definitely. I mean. For example, when we get some great results on the training or displaying how we train or examine the data points, that is really interesting. So let me check the Kristaps. So let me find you. You say that I did not grade, but I did. So which one? Not handed in. Really, in the classroom, I see that I have graded all of your first homeworks. Then the second homework, it shows me that it is not handed in at all. So maybe you added it. Okay, but okay, it is handed in. I don't know like how it slipped by. This is really strange. Maybe you did not press some button or something, but yeah. Okay, I will check that. Thank you for letting me know. If somebody else have disputes with the grading and the submitted homeworks, let me know. I will double check, because as it seems like that the Google Classroom did not show that one as resubmitted, even though it was there. So maybe it was not pressed the button that you submitted. So anyways, we'll not like waste time on this. So, and then later today we'll start looking at, so this was like our brief intro in the Pytorch, and then later we'll start looking at classification task, where we will classify irises. So we are in the spring, so we would like to see nice flowers, and basically by dimensions of the leaves we will classify which class is the flower. So again, data set with 4 input values, right? These lengths of the leaves, and then the class of the flower. So the class can be 0, 1, 3, 0, 1, 2, or like human terms, setosa, virginica, and stuff like that. So anyway, let's move back to the code now and finish the Pytorch part of the regression task. So my first part of today's tutorial is that on the workshop is that we will convert the Numpy based model using the same skeleton. As you see in my template, this is the same skeleton for yesterday, but using now only the Pytorch. And we will of course not cover things that you have to do in homeworks, so you will still need to implement those that I asked you yesterday to implement. So here let's then do the model. So one thing that's missing, we need import torch in top of the part. So import torch. Hopefully you install the torch. If it's not installed, then you can go here and press on terminal and conda install torch, Pytorch. or something, you can look in the pytorch.org, I think, or .com, or what was the correct syntax for installing in Conda. A very easy process. So you can install if it's not there, but it should be there, because Hello World, I think, double check that you had that one. So anyway, let's start writing the code. So we'll have the class model, and I need actually remember that I need to look what was the previous code, so I can make it as close as possible, not as close as possible, but basically we can copy the previous code and make it in the Pytorch that was previously done just clearly in Numpy, or how I like to say it, by force of the hand. So I mean, like, or brain, basically, because you need to work with brain to make that one. So anyway, the Pytorch will make life a lot easier in some sense, and make your logic in a much more complicated in other sense. So it will make give you capabilities that would be really hard to do just with the Numpy, but still the math will be there. So okay, so there is a model. Oh, sorry, the model is inherited from torch.nn module. So every function, even the module function, like the model itself is also a function, of course. Like if you have many functions inside, like in the list or in some other function, that is still the function. So any function in Torch is torch.nn module, starting like from model, from sigmoids, from linears, from loss functions, everything is module. So then Torch, I mean, not Torch, but def init. And here we need to initialize, also definitely need to initialize the superclass of the parent class, like that. So that's good. Then we will start constructing our layers. So self layers, exactly as it was yesterday, but here are some caveats. By the way, the code that we are making, it's like one-to-one as we already made ourselves. So here will be torch.nn sequential. That is a container. So we could definitely code self layers as just a simple Python list, but the other function that we yesterday made, if you remember, there was a function called parameters, right? That is actually implemented already in this torch.nn module. And this function parameters that we don't need to implement today anymore, because it's already provided in the base class, looks for containers that are inherited from torch.nn. If this is just a list, it will not look inside that list and will not find the linear layers. As you know, yesterday that we were looking for linear layers inside the parameters function. So let's add here some comment, so that will not work because parameters will not find linear layers in non-torch containers. So that's one thing. Then the other thing, so we can add those layers. So torch.nn linear, I think it is just a linear like that, so it's without the layer here. So in features, and if this is a California dataset as it is, we know already that in features should be 8. Out features can be anything we want, but let's add 4. So like it was exactly yesterday, so I don't want to make anything different. So, but you can make it as you want. So here we can relu. By the way, again, the relu is kind of function without any parameters, so it's kind of not definitely necessary to add in constructor. In constructor, in this part of the code, we need to add only things that contain parameters that can be learned, but in torch relu there is no parameters, so theoretically we could not add it here and just use it in forward pass, but it doesn't matter here. For this case, let's leave it as it was before. So then let's copy these two lines again. I think we need to copy twice and delete linear at the end. So here will be 4 to 4, 4, 4, and then at the end we want to predict the price of the house, and that of course is just one-dimensional stuff. So okay, like that. So this is done. Then the next part is that we need to do is forward pass, just as we did before, multiple sessions already. So forward pass will be self x, right, like that. And in the forward pass we can either go through in a for loop to this container, but this container is very nice because it already have the implemented the forward pass, so we can have it like this. So y prim is the layers forward x. By the way, in the Pytorch, of course, there are some overridden operators, like like, is it called operators? So you could call these functions directly in this manner, like y prim is layers x, like that. But please don't do this, because if you do this, this makes impossible to understand if this is a function or this is an instance. So of course you can override yourself if you want this stuff, like def call, there is a call this operator, and you pretend that your class instance is a function. But please don't do this, because the code then is not readable. So if we leave the instance and then leave the function, then at least we understand that this is a container or instance and this is function and not something in between. So okay, we have this one ready. Then the last part here is that we need to we don't need to have the backward pass. So we can have the backward pass, by the way, backward. So we can override the backward pass for the Python, and in some cases that's useful, especially if you have like a really interesting type of models. There is one case where you could use it in reinforcement learning for policy gradient. So anyways, you can override the backward pass, but you don't need that one at all, because the torch, the Pytorch have something called auto-grad. Do not, so let's add it somewhere, comment. So backward not needed, because Pytorch has auto-grad. So, and the auto-grad or the auto-differentiation engine just takes the tables of the derivatives and applies them in an algorithmic way. So the end result derivative might not be like, when you derive it and like have the equation written very nicely for the human to read, but still it will have the same mathematical solution, maybe in longer equation, and it's something that is done mechanically, because of course the derivative tables is not something genius. Any person can just take derivative tables and place them inside those equations and get derivatives. So that is the way how it's done with Pytorch, that you actually don't need to calculate derivatives yourself, but in most cases. But any action that you will do with the tensors that we will just start working now will have the pointers to previous function, and then it can calculate gradients to any path of the calculation. So that's quite cool. Anyway, and we will just see in a second what I mean by that. So I will add this part of the code to the Jamboard, so you can catch up with this part. I hope that I don't have errors, but if I have, then we fix that later. So this will be in the slide 2, and we'll move to the next part of the implementation down the road. By the way, if you have some questions so far, let me know. By the way, there are a lot of functions implemented already, but we will implement a lot of new ones as well. So this is our model. The model needs to be initialized, of course. Now we are missing the one part that was linking everything together. So one is the model, right? We need to initialize it. Then the other one was the optimizer, right? We had the optimizer, but now we could use some more advanced maybe optimizer. I don't know, like we can talk about optimizers some other time, but torch NN, I mean torch optim. Okay, here we have quite a few optimizers that we can try out. For the, like, generically, we could use ADAM, but like there is also implementation of RADAM, but it's not here by default. So the RADAM is like go-to optimization for today. So it was published, I think, 1 or 2 years ago, and that is much less sensitive to the learning rate and stuff like that. So, but you can use all sorts of optimization algorithms. Of course, you can use also SGD, so the stochastic gradient descent. Maybe we could use that one, but I just want to have really good results quickly. So let's use ADAM. So, and here we have some parameters. So first one is the params, and the params we can get from model parameters, exactly like we did yesterday. That is exactly in the homework. Then the learning rate, again, exactly like it was before, learning rate. By the way, the learning rate probably, I don't know, like let's leave it as it is, but maybe it should be smaller. So then the optimizer is ready. Then we need the loss function. For the loss function, I don't want to implement it here, and I definitely prohibit you to use like ready-made loss functions inside the Pytorch, because that part is really trivial and at the same time really powerful for understanding how these models train. And please don't use the built-in loss functions, especially, for example, for classification. As I always see students just pick cross entropy and make completely wrong models, because if you don't read like how they are implemented, you can have really wrong results. So anyway, we will not define loss function here. We will go down here. So, and I will add also those few lines. By the way, we are really close of running the model. Basically, we don't need to even calculate derivatives and everything, so its life becomes so far a lot easier, and then it will become a lot harder again. So here, let's see, we'll have the batch. So in the Pytorch, there is actually a better way how to do the batches. There is something called data loader, but we will not use it for now. I just don't want to confuse you too much. So here, torch torch float tensor. So we will make a float tensor here of x. So, and we will pass it inside the y prime. And as you see, again, this is very crucial. Here we have the variable, and we are changing that to float tensor. So float tensor acts as variable. So that means that each float tensor have value and grad. So each float tensor have a value, or it's called data, and grad props as variable head. So this is exactly the same approach that we implemented yesterday. It's important to understand how it works. So then the next part is with regards to the loss function. And now the beautiful part, I think that's why it's also, I don't recommend you to implement loss functions by already ready-made ones. So here you can see that you can directly write your equations. So, but again, I need to also convert the y, just a second. So y will also be torch float tensor of y. So here we can write equations directly between the variables like we would do in Numpy. So here, let's say torch mean, like that. And this is something to think about, because this is very important. So when I do this equation here, it automatically tracks every single mathematical operation starting from y prime, what is subtracted from what, and so on. And at the end, like we will integrate, we will differentiate, how calculate the partial derivative from the loss function with regards to the each of the weights and biases in the model. So here, when we call the loss backward, it already knows how it looks like the loss function, and it already knows all of the path. So starting with the mean, then the squared, then the minus, and it can go deep inside our model till every weight and calculate the gradients along all of the path. So this is not just a simple mathematical operation here. So, and this is achieved by overriding all of these operators, minus and the squared and everything. The same way as I showed you before, that you can override the call function, you can override, of course, def add, for example, the addition and everything else, and the Pytorch has done it. So every variable or the float tensor have overridden all of these operations that you would use as mathematical operations, and then they use those overridden operations for calculating the derivatives. So that's why it works. So here's the loss, and there is a backward, and there is these things. And I think that's about it. It should be done. So let's try to run it. Okay, there is a small problem. So yeah, the fun thing is that for this kind of operation, as I just said, we don't need to call backward for the model, because these variables or float tensors already know the path to each of the weights inside the model. So we don't need that line at all. So we'll try again. Hopefully it will work. Funny why it's taking so long. Okay. There is something happening. Strange. Okay. And then I forgot another thing, but in general everything is fine. So the other thing is that as we already talked many times, we have different types of data, right? We have the let's say we have the lists, right? Lists. We can convert lists to NP array, right? The Numpy array. Then we can convert back to the list, or we can convert to the torch float tensor. And if we want then to operate with NP here, as we did with the NP mean or something, it works only with these two and not with this one. So we need to go back in some way. And to go back in some way, there is one option is that you can access it like we did with the variable dot data or dot value as it was. That is one option. Another option is that if you have just one singular value in that tensor, there is a function called item, like that. This is the same as it would be, so the item is the same as it would be like this. So this should be the same output. Okay, let me try to run it. If it will work, I will then submit the code to the Jamboard. Now it works a lot slower than I was expecting. But anyways, hopefully it works. So I see that the loss is reducing. And hopefully we'll see also the plot just in a second, and then I will add it to the Jamboard. Is it reducing? It's not reducing. Fun things. So it's jumping all around the place and it's going really slow. That is really strange. So I think one reason could be that the learning rate is crazy high for this kind of, for the Adam at least, maybe for the SGD that would be fine. So let's see, if I add learning rate E minus 4. And I will also check if I don't have some other bugs. So let's see. Now let's run it again. We'll soon also start working with GPU, and with GPU everything works a lot faster. So okay, now the loss is reducing a lot better. So now it's a consistent. So with these fancy optimizers like Radom, and all, like Radom is not so bad, but Adam and RMS Prop, they like to have these. They like to have the learning rates a lot smaller. So here, basically, we converged very quickly. So even in the second epoch, everything is already with a very small error value. So what we can do again is maybe we can reduce it even more so it would not converge that quickly. So E minus 6, let's see with that one. By the way, meanwhile, while I'm experimenting, I will copy this part of the code to the Jamboard so you can catch up with it. And then I will give you the proper learning rate as well that you can try out. So this is basically the same code as before, but a little bit more advanced using the Pytorch. So now I'm running, okay, with E minus 6 it looks smoother, not giving the perfect answer just after one epoch, you know. So this dataset is not so difficult, that's why it is happening. So let's add also these hyperparameters to the Jamboard so you can fit them. Okay, the loss is reducing, and it's the way how it reduces maybe not that cool, but still. So I don't know, like maybe E minus 4 works better because like it's still quite large values. Anyway, so let's see how it will work again. Let me close all of my plots. There are a lot of them. Okay, it will probably show another plot in 40 epochs. Okay. Yeah, so I'm not sure like why it's so slow for me right now. Really not sure actually. It should not be that slow, but still. Okay, so is the code running fine for you? Plus, minus. If there is some problem, let me know what kind of problem do you have. So I see 4 pluses coming in. Hopefully everybody's getting along. So right now we are seeing not exactly overfitting, but more as something like called catastrophical forgetting or something. Is there a way to estimate good learning rate without experimentation? So the best way would be to use some kind of smart optimizer that tries to minimize the effect of the learning rate and also build your model in a way that is minimizing the effect of the learning rate. Otherwise, then you need to do the grid search basically. So the grid search is all dependence, like full factorial between all of your hyperparameters. Yeah, so that's the best what we have right now. And Yeah, so the model is really simple, very weak one with 8441, so probably that's why it is starting to forget some of this stuff. But still, with these kind of like loss plots, we cannot tell how good the model is working, because it is giving us the mean square error. I mean, yeah, mean square error. So we cannot really tell like how precisely our model is working. Like, is it is the error like 100,000 of euros of the price, or let's say 2 like or 5 euros of the price? So nobody can really tell it just from looking at the loss lines. Of course, the one way you could maybe have the square root, but then again the problem is that we don't know what is the, with regards to the data set. Maybe in the data set we have, let's say, our like standard deviation between our house prices in hundreds of thousands or in millions, or maybe in a few euros. So all of these cases determine how precise our model is, because if there is hundreds of thousands of difference between the prices, and then the error is just in a few like hundreds, that is like much better situation. So anyways, to estimate this, I propose that we could use something smarter. So there are multiple ways how you can calculate normalized. So there are actually other metrics like R2 score and stuff, but those metrics also have some caveats. But so we need some other metric, basically what I'm saying. So let's try to use some other metric that we could apply for this task. And the other metric will be called normalized root mean square error, this kind of equation. And with this equation, the first part of the equation with normalization part that you already coded in your homework is, so this can be also the standardization part with standard deviation, and there are few more variations. So this kind of metric can be calculated at least, I think, in 2 or 3 ways. Maybe there's even more ways. So it's just way how to normalize the root mean square error, so that the output that you get is something around like 0 to 1, and 1 means perfect and 0 means bad. So that is what we want. Otherwise, we cannot really estimate which values are good or which values are bad. So let's say 0 is bad, 1 around 1 is great. So that is what we want as our output of this metric for the scalar values like prices and stuff like that. So let's implement this equation then, also here in our code. And I will probably give you some metric, not probably, but definitely give you some other metric as a homework, but that will be for different tasks. We will need to live to that. So here, let's add these ones. So there will be 2 additional holders. So not loss, but let's say normalized root mean square error and NRMSE. So these will add here. And also let's add something like that here. And with the S's. And then we calculate that one over. So there's another small caveat to that. Maybe I definitely should show you that also here. So here, so there will be NRMSE here calculated, and then we will add that one to the list. And here we'll do some very important hack. So not hack, but operation. So we will do the detash. So the detach means that from now point on, from this line where we move this variable y to a new variable y here, or maybe we could call it, I don't know, like y detach or whatever. So we will not calculate the gradient anymore. So that, as I said you before, that in all of these equations we calculate which function was before that function, and actually you can access that operation by having y fn, I would think it was fn grad or something like that. You can access the previous function, and in that way, when we have the loss backward here calculated, it will include everything that's done with these functions, and it's very important. If you don't detach them, they will include also all of as your loss function, also your metrics and everything that you calculate after your loss function or before the loss function. So that's why we do the detach here, and we also do the detach for this one. So that means I want to disconnect the partial derivatives from this moment on. So these are disconnected now. Now the next decision that we need to make is with regards to calculating the normalized root mean square error in terms of either the dataset or the batches, probably the dataset. So, and there are two datasets actually. So, and I don't want to. How could I do this quickly? So this will be not optimal code at this moment, but I need to do this because otherwise maybe I can do it up here probably. Okay, so I will do it up here so that it is in the same screen at least. So here we'll have the y yeah, but that is the train and test. Yeah, we can do this, no problem. So y max will be then the data set. So this will be y max train. Okay, let me see y. Let's how we could call it down. Okay, y max train be that dataset train one, and from this is still a Numpy, so we can have it np max. And by the way, this is one dimensional, that's why I don't need to have axis and stuff. So this will be 1. Then we'll have the min for train. Then we'll have the same for test. Okay, that's good. So we have all of those coming in, and then I would love to add them here in this line, but let's not overcomplicate this. We need to get them here. So probably let's add some if statement just to not complicate this. So we'll have the scalar. So the scalar will be 1 divided by the y train max. I mean, this will be test, actually test minus y min test. And then if we are in the train dataset, we will use the scalar as the train. So that's good. By the way, you can write this code another way as well if you want, because the equation is still the same. So this is coming in as a scalar here. Then we multiply this by torch sqrt, and then have the so torch mean of the same equation that we had before, basically. So we can actually use the loss here Yeah, so we can use the loss here. That's great. So we can add the loss here, except again the loss should better be detached. So okay, so we don't need actually these two lines then, but it's great that I explained you about the detach. But maybe it's so you can write it as this, or if I write it as this, maybe somebody will be confused. That's why I will copy the lines better. So this will be better. Okay. So far, hopefully so good. I will double check if there is no bug, and then if there is no bug, I will add the code to the Jamboard so far, and then we need just to add to the plots those normalized root mean square errors. Seems like working. So this is working. I'm adding this to the plots. Not to plots, but to Jamboard. So the Jamboard added that part of the code, and now we need the last bit is just yeah, thank you. Kristaps is telling me correct that I forgot to have. So if I don't use the loss function here, I need the mean here. That is correct. But you could use the loss with the dash also here. So that is correct. I will copy my mistake, fix my mistake, add it to Jamboard. Again, as always, maths usually work, like in many cases, work even when they are wrong. So that's why you should know how to write them correctly. So normalized root mean square error train and test, I have those ones. So here we can have, and I forgot also to have this as an item, unfortunately. So I need to update it third time, the Jamboard. And then we add to the plots, and then everything should be fine. Hopefully we will not see bad results. Hopefully, I did not test this before. So, but if we get bad results, we can improve model, and then it will be good. So normalized root mean square errors, adding to the train, adding to the test, like that. Except I don't like that this time I added in the second line. Let's move it to the first line. So these are added here. And now we need to add to the plots. So we can add, let's say, two plots. So plot, subplot of, so two lines, one column, first plot, then the second plot. And the second plot will just have all of these guys. Train and test. No normalized root mean square error. We can add also some title. This is an RMSC, and this is plot title of loss L2. So okay, if I run it and if it will be okay, then I will add these lines also to the Jamboard so you can catch up on them. Okay, I did not actually add so that my plot is drawing every time I run it, only after 10 epochs. That's not optimal at all. In this case, we didn't want a lot of plots, that's why I didn't do that. So anyway, I will move this code also to the Jamboard. Okay, normalized root mean square error. Sorry, I did mistake. So nobody corrected me. That's also fun. So we can go back to the Jamboard and fix my mistake. So my mistake is that, of course, error. This is not accuracy. This is error. So 0 is great, or about close to 0. Actually, yeah, 0 is great, and like around 1 or a little bit more, that is bad. So it's actually also not that precise, but still, like, so it's from 0 to around 1, but it will be over 1 probably, especially if the error is a little bit higher in the beginning. So that's why it's reducing it. So the error is actually really high. That's why it's not even in 1. So that we need to wait a little bit longer until it gets smaller. So I will probably change the learning rate because I don't want to wait so long. And I also will maybe do print after every second epoch and run it again. Let's see what we get. Yeah, so values converged immediately and I don't see much. So let's e minus 5, and then I also don't like that I don't see the actual values, so I can add those values as well. If you want, you can do this as well. In general, the model, the code is ready, but we just let's clean up a little bit. So here, the train minus 1. And again, the dataset is very simple. That's why it converges immediately with advanced optimizer. So with this one will be the test, and let's see. Hopefully we'll see something closer to 0, under 1 at some point. But now I added e minus 5, so let's see how well. Okay, so this is 0.4. 0.3, really nice. So with e minus 5, actually the training is so much nicer. So okay, oh man, I did not show the code, sorry for that. So with e minus 5, the code, this is much nicer, and I also added the prints here, so I can print the values. I will update a little bit the Jamboard, so you have the latest stuff that I have. Of course, all of this is optional. It's not something that you definitely need to have. By the way, let's see. The learning rate should be e minus 5 for this model. This would be much nicer results. If you just have larger learning rate, it immediately converges and there is nothing interesting to see. And also, sometimes immediate convergence might lead to not the best result, but let's see. Okay, so now it's smoothly learning the things, and the error is reducing. It's actually proportionally reducing to L2, so that's great. But the best thing is that we can evaluate it. So if it's in the range of 1 to 0, that is our range. So if it's over 1, this is super bad. If it's 1, this is bad. And if it's like close to 0, this is great. So we want the values, so you can think of kind of accuracy. So if it's like 0.1, that's kind of like 90% accurate model. So that's what we want. Okay. So we're done, hopefully, with this. I added to Jamboard also the code. So is the code ready? Plus, minus. The loss function in negatives, that's fun. So probably that means that you have some mistake in your equation, because if you have correct equation, then the L2, the parabolic function, cannot go in negatives. If it goes in negatives, that means that it's not parabolic function, at least with staying over 0. So I see that Christoph is saying plus. Let's wait for some other people, and then we'll move to the next section of our today's workshop that will be also quite intensive. So I see some questions. Every time I run it, the result is different. So that it could be possible, the initialization of the model and the high dimensional manifold of this these weights. This means that you cannot really ensure that every time you have the same output. How do I attach the plot window to Pytorch? So for me, it's done automatically. I'm not sure why would it not work for you. The other way is you can do with these backends, as it was in the first, like the asteroid game. So you can add backends as you wish. And if you add some backends, it would show not in the Pytorch, or it would show in some other part, but probably there is one backend that is connected to this window in Pytorch, but I don't know that one immediately. I need to look up then that one, but that's a technical question. Hopefully, if somebody else knows the answer, you can help out. So now the next part. So please get the template 8.3. Please get template 8.3, and when it is ready for work, type in plus. I will also drop the template in the Mega just in a second. So we'll start working with a new dataset. The dataset that I gave you introduction in the very beginning, that was for identifying the class of the flower based on 4 features of the sizes of the leaves. So the template also available here. Okay, sorry, I'm opening that one. And let me know when you're ready, and then we'll start digging into equations first and the logic, and then afterwards we will implement these to-do parts in the template. Most likely I will help you out implementing some parts of those. I could probably leave it as it is, but I'm scared that maybe it would not work, and we need to do this in 1 hour, so that would be a challenge. So now let's start doing new chapter in our exploration. I will go to the Jamboard. We'll try to find this this image again, because that's quite typical image. I really like that somebody made this image. So this will be a classification task. Before, we worked with regression task. Regression task was for identifying the like prices or scalar values or the vector directions or something. So this is for classifying the data. So classification task. And to formulate the classification task, we need to do a few things. So one is that our dataset, if you would look inside your dataset, it would contain the X as shape as the n samples, comma 4 features. That is easy part, no problem there. So the same as we had with the housing, where we had 8 features. The Y shape in this case is also kind of the same as in housing, like that. And each of the elements in this Y is the index for classes. So Y0 would be, let's say, 2. This is IDX class class 2, and that means that this is a third class, and this means it's like a Virginica or there is a 3 class classification. And then let's say Y1 sample is 0, and that means this is a setosa, and so on. So these are the classes of the flowers. So is it clear so far? Is it clear so far? Plus, minus. If something not clear so far, let me know. So I see 2 pluses. Okay, more pluses coming in. Okay, this is slightly off topic, but do you receive emails if you add comment submissions in Google Classroom? I think I get those emails of the Google Classroom. Yeah, definitely get them, but generally when I do the grading, I just look for all of the students who resubmitted the tasks. So make sure you press resubmit button, and then you add comments. If you add comments after I already grade you and you do not resubmit anything, it's possible that I might pass that comment, not see it, because there's a lot of work for me to do to grade others. So be mindful of that. If you have some specific questions, like with regards to models, research, or something, you can write to my email, definitely, directly. And of course, later when we start thinking about some serious research together, maybe for your bachelor's, master's thesis, or so on, then we can have even meetings. So, okay, here we have these pluses in that you understand. But there is one thing. So the models that we train, we never train it with these indexes. We always train each of these samples. So Y prim would actually look like this. So the Y prim, the prediction, for example, will be 0%, 0%. So this will be probability distribution, 100%. And then the Y1 in this case will be, first one will be 100%, and those will be 0%. And of course we can rewrite this as one hot encoded vector. It's called like that, where it's like just with the floating point values, right? Like that. And this is the way how we actually predict those outputs. Is it clear so far? And so yeah, first question, is it clear so far? Plus, minus. And also Maybe another question I should start with that is, why do you think probability distribution is better than predicting index? Why this way of predicting probability distributions is better than model that predicts the index itself? The answer is mathematical, by the way. So, by the way, if you don't have any ideas, then minus. If no ideas. So the answer involves the distances. Wow, that is so nice, unexpected answer. So Kristaps is saying that because sometimes flowers cannot be 100% looking as some specific flower. That is really nice answer. At the same time, with regards to 100%, is that the loss function that we're gonna use do not work with like 90% accuracy and something like that. So the model can predict that this is 90% accurate, and this is something that actually happens in reality, but the ground truth cannot be 90% accurate in that particular loss function that we will look at, because of the theory that is tied to how it's derived. So that was not exactly the answer, but that's the interesting direction of thought. So we can estimate how accurate this model based on how close probability we got, right? So we can estimate the class also based on the scalar value, of course. The probability distribution gives us some values to work with. Prediction goes blindly. Probability distribution gives us some values to work with. Prediction goes blindly. So I don't know. Like, I mean, it could be possible to limit the outputs and to squeeze them in the range of, let's say, that 1 to 2, and kind of from 0 to 2, and make sure that we can kind of round the indexes and stuff. But all of these answers are interesting, but they are not exactly what I mean by that. So one of the reasons why the probability distributions are go to way here is because it's mathematical. Because if we look at the distance between, so the distance, if we introduce some kind of distance here between the indexes, so distance between y and y1, and so this could be L2 distance or something like just like ABS distance, or we can maybe write it down somehow. So minus y, so that's 1 and y0, and then if we, let's say, square it, right? So this distance is larger than, if we look at the y0 and y2, right? So if you think about it, that distance, basically the outcome of calculating the values is larger, but at the same time, every class should be the same, should have the same distance in between them in the outputs, because otherwise we are kind of tied to some kind of specific mathematical region for each of the classes. And in this case, if we look at this, this is the same. So y prim here would be the same. So in this case, between any two classes, we will always have the same kind of distance. They would not be located in our function, some, like, for example, that this class is definitely closer to 0 than this class. And basically now we have some kind of way how we can encode our vectors in a way that their proximity is not based on their scalar values. So do you understand so far? Plus, minus, if you don't understand something, let me know what you don't understand. Okay, we have some minus, but some pluses. So the idea is that the output, like the class index, should not determine mathematically that, for example, if this is the first class, then the output should be so the model itself. If you think about the model have the linear projection, the last output. So the linear projection should not be biased towards some specific scale of the scalar values just because this is specific class. So it's much better than all of the like the embedding space, as you think like that, so that these class vector space is distributed evenly in this output. That's why it was one reason. But we'll move on. So even if you did not get this reason, there are more reasons why there should be a probability distribution. So in order to get, first of all, the probability distribution, we need to apply some extra function, because of course the linear outputs of the model never gives us the probabilities like 90% and something like that. So here's an example that the last linear layer will give us vector of, let's say here, 5 classes. There are 5 class vector. So this is 5 classes. In our cases we have 3 classes. Then we apply the function called softmax, and then we get the outputs of the probabilities here. So there is even more to that, because maybe I need to also show how it actually practically looks like. Maybe if it's hard to imagine the last layer, but probably not. So the last layer looks like that. Then I will try to look up some more equations, because the softmax has some specific reason why you would like to use softmax and not something else. Because the best way how we would then, for example, if the only way basically that we would want to work with indexes is if that would be hard max. So the hard max function looks like that. And you already used that many times in our course. So that this idea is that you would select the index of the correct class, and then this would not be dependent actually on on the so we are not predicting the index itself, but we are selecting the index from probability distribution. And in this case, this would work perfect. But the problem is that a hard max or the argmax, we cannot calculate the derivative to this kind of function, and that's why we want to use something that is also smoother to converge. There are some options what we could use. There are, for example, there is a norm max or the simple normalization that you can use by summation. So that's like the most simple one that you can imagine, right? To make everything like normalized, right? And then there is the softmax, right? The one that you already see on the screen. And the softmax, if you think about it, if you plug in the values, gives actually the values that are most close to what you would get with hardmax. Maybe there you could, I'm not sure, like how like you could rearrange. Maybe you can rearrange something that gives even higher, like these values that is still tractable, and you can calculate derivatives to that. But if you look at some example, you see that the norm max, there is not much difference between those like outputs and the probabilities that have similar, like the range, like 2 to 4 to 2 to 1. But if you have the softmax where you have the exponential function, then of course this is a huge difference there, and this is much closer, similar to the hardmax. And this is another reason why this approach of the softmax works well. So these are much more similar. And but still, of course, like, so the main reason why we use softmax is that we want to ensure that this is a proper probability distribution, distribution. And in order to this to be ensured the proper probability distribution, we need to have sum of p as 100% probability if we sum all of the probabilities of this distribution. So this is the main reason why we want to have this softmax here. So then the next question is how we train that one. And the answer is that we use the information theory. So in the information theory, there is one thing called, so let me share while I write the equation. So there is a categorical cross entropy, and the KL divergence and other stuff there. So the idea how it came from the information theory was that they wanted to estimate the losses in the bit translations, where you have some kind of digital radios, and how what is the probability of the losing some information on with specific number of bits. And at the end, like, this kind of theory came all the way to probability distribution calculations in the deep learning. So here we have the categorical cross entropy, the most simplest one, where, as you see, this would work if it's written in this way, only if the y vector and y prime vector both would be probability distributions. And of course, we already know how to do this, because we implemented because we just talked about it in a previous slide. So this is one. Of course, we need to calculate then derivatives with regards to this one. So again, what we would need is to have the partial derivative there. So let's see. So we need the partial derivative with regards to our loss function. So maybe we can try to copy it somehow like this. And if you know the derivative tables that you can look up quite quickly, the derivative with regards to x from logarithm is 1 divided by x. So that stays the same. So basically, if we just drop the sum and mean, but it doesn't matter, we just can leave it back as it was. So that would be frac over, so this will be 1 over y prime and multiplied by y. So again, we calculating derivatives, so like that, and then the output, of course, is just minus y. I guess like we can just leave it minus in front. So that would be derivative with regards to the y prime. And also, I guess this loss function have quite a few like names. I think they sometimes call it negative log loss or categorical cross entropy or cross entropy. There are a few ways how you call it. Also, there are a few ways how you calculate it, because if, for example, this is not probability distribution but just an index, you can select your index directly from probability distributions and leave out this term completely. That is also possible. So, okay, this is this. And the one thing that's still missing before starting to code is that we don't have softmax yet. So then we have the softmax, but we don't have the softmax derivative. Just a second. Let me add those equations also. So where I lost it a little bit. So this was derivative, right? And this was derivative. Then let's add the softmax here. Oops. So let me look how it looks like. So the softmax is a very tricky function, because now we have there are a lot of pairwise operations. We have exponents here, but at the same time there are the summation for k, and the top part there is a j. So it would not be that easy now to go through each step here, but I will give you like just a like matrix of that derivative. So that would be called Jacobian derivative, where you have we already actually had those, but we didn't call it like that. But the idea is that you have interdependence between all of those pairs in the function, and the only way how to properly calculate derivative is to calculate for each of the pairs in the matrix, and that would look like something like this. So this would be, and the A is actually the output of this softmax for that particular cell. So here that would be the derivative, the softmax. Probably I should rewrite this equation a little bit clearer, but the A is the output for each of those cells. So what I mean by that is that the softmax will produce the probability. So there will be A0, A1, and A2. So this is the output of our softmax function for this example of three classes. So, and then if we calculate the output of this one, and then plug it in this matrix of the Jacobian, then we can have, this would be considered as the derivative of softmax with regards to the x, and we can then multiply that with the dot product. We could dot product that inside our function graph. So we will go back to these equations just in a second. And now we need to go and try to implement them. And in home, you will need to then implement the same thing in Pytorch yourself. But now we'll do the most difficult part and show you how to implement this with the Numpy. Actually, in some other courses, I have asked people to implement this themselves. I kind of see that sometimes people do not understand it well. That's why maybe we'll go together with this one. So let's go back to the scene. So here we have the code. The code looks very similar to what we had before with the Numpy-based regression of the house prices, but now in this case we need to classify, we need to say which class is correct class for this iris dataset. This is not the same task as before when we had the regression, so that is one difference. So if we go down to the model here, so we see that there is missing softmax implementation. This is one part. Cross entropy also missing, and then we need to change model also. So I believe that to change the model, that is the most easiest part that you all should be able to do now by yourself. But the implementation maybe on the class, I mean the softmax probably is a little bit more difficult, but we can do this together, and I will also walk you through some caveats to the numerical stability. So here, let's see. So we have the softmax here, so we need to implement that one. Let me think how to implement it better. One thing that I want to have the copy of the X. MP, was there clone or copy? Yeah, there is a copy. So the copy is basically the same as the array, but I just want to make sure that this is clear. So I want to copy the value, and you will see just in a second why I copy that value. So then, if I calculate the function itself, I believe all of you should be able to do this also quite easily now. So this will be then the so this will be the variable of course the variable that we need to calculate. So the top part contains the NP exponent of the MPX, and the bottom part, so this is really the simplest part basically. So the bottom part is then the NP sum over again those same x's, but just summed together in particular manner. So they are not just summed all together, they are summed by the axis 1, so that means they are summed for each of the samples. So basically, if there would be no axis, we would mix together all of our batch, because we have this shape of batch, comma, classes here, or the features. So we don't want to mix all of the sum of the probabilities of each of the samples in the batch. We want to look at each of the samples separately. That's one part. The other part, I also like to keep dims here. I think the division would be correct only if I keep the dims here. So that's fine. But if there arises some problem. So imagine, let's do some experiments. So if I have the exponent function, so exp function, and if I add in the exponent function, so let's write here exponent function of something like 0.1. So that could be reasonable. So the 0.1 output is around 1.1. So then if I add something like exponent of, let's say, 100, the output is crazy large. And then like the 100 actually is really small difference in general from like 0 or 1 or something, but the output is like this. And if I keep adding, so there's nothing limiting. The linear layer can return some like thousands. The linear layer can easily return something like exponent of let's say 10,000s, like that, or 100,000s, so 10,000s, or maybe let's say millions. So let's see, 1, 2, 3 millions. So let's see what happens if I do that. So what do you think, what will happen if I feed there, or let's say some 100 million? So what would happen if I feed 100 million in exp, and what could we do to avoid this? Good answer, infinity. But also it would be nice to see what we could do to avoid this. Divide the number in the brackets with itself. Deny the number with the brackets with itself. You could do that. You could do that, but maybe not the same result coming out. Then we can set the ceiling. That's maybe that's by the way not the worst idea. So I mean. We want to have the same answer after this equation as it would be with some kind of limits, but really without that much limits. So there is one numerical hack often used. Actually, there will be two hacks that I will show you. So one hack is, that's why when I use the copying stuff here, is that we want to, because the way how exponent function works, it works also when we reduce the maximum value of those. So let's see if there is some maximum value, and if I think, let's see, it could be not maximal, it could be also, let's say, probably, maybe it would work with some other equation as well, but usually they use maximum. So you can use the maximum value to remove that one from the input, and you would get approximately the same output as before. If you don't believe me, you can test it. But there is another problem now. So this is one. So numerical stability for large values. And then the other problem now arises that using this hack, we have very, very small values. And if we have very, very small values in x, then also this is not great, because then we would have something like exponent of like floating point with a very lot of zeros, and then it can round down to 1 or something. So that's not also like optimal. So I would advise to add some kind of epsilon here. So e minus 8. So we have two hacks here to ensure numerical stability. So that's fine. So the next part is then derivative. So derivative is the fun part. So here we can calculate the Jacobian matrix, or the basically derivative that is containing as a matrix. And if you think about it, we already had those before. So I will copy that in the Jamboard in a second, but I just want to show you. So before, the weight matrix gradient also was the derivative of the matrix form. So this is the same idea here. So we have J here, NP and I will make a template for this, but basically there are shorter ways how to write this, but if I write it in a shorter way, I'm afraid that somebody might not understand it. So I will try to write it in a semi-short way. So probably you can write it even longer way than I will do this now, but still. So let's call it as an O, the output, as it was in, or the A, we can call it maybe an A, that, like it was in that equation. Let's call it as A. So self output value. So that is the A as in that equation that I showed you on the Jamboard. So then we go over rows and columns. So for E in range of 3. By the way, let's ask some question, sanity check here. Let's do some sanity check. So why do we have a batch by 3 by 3 matrix? Why exactly do we use number 3? Dimension 3. So that's my question. And meanwhile, I will just write these 2 lines of I and J. And then I'll wait for some ideas. So, and if you don't have any ideas, no ideas, type in minus. Just want to do some small check. Do you follow me on this part? By the way, we are not so far for colors. Okay. That's so it actually was hopefully, I'm not sure actually. What you mean? What do you mean by for colors? Need to a little bit clarify the answer, or give me minus if you don't understand why do we have 3 by 3 matrix here. Okay, so we have another minus. So the number 3 that we have, that is something that we already looked at the slides before. The number 3 means that we have 3 classes, right? So if we go quickly back to the slides, and because that's kind of essential understanding, this just like basic knowledge of what we're doing. So here we have 3 types of classes, right? So there are many samples. There are 150 samples. Some samples have the same class, so 2 blue colored flowers, then red colored, then some kind of other. So hopefully Kristaps meant colors, but these are normally called classes. So we have 3 different types of classes. Maybe I need to write it down. So 3 different types of classes. That's why we have number 3 in that equation of that derivative. So then we pass it to the probability distribution, and from this we get out also. So here we have the probability distribution of the softmax, and you get 3 different probabilities for each of the classes of the flowers. So these are the probabilities of classes of flowers. And then if we calculate the derivative with regards to x for softmax, then we get this matrix where we have what we will then later use for getting this vector of 3 error for that vector. So, and the vector, if you have 3 by 3 matrix and you multiply it by, not multiply it, but do dot product with 3-dimensional vector of that will go after this function, of course it will get again 3-dimensional vector. So, with regards to my question, why do we use through the dimension 3, is it clear now or not? Is it clear why do we have 3-dimensional vector? Again, if you think about the way how derivatives work, and then with the chain rule, the input for the next function, that is the cross entropy, will be this three-dimensional vector, and then the derivative also will be three-dimensional vector, and then we will dot product it with this 3 by 3 matrix, and we will get next three-dimensional vector for the previous layer. That is how it works. But is it clear why we need at all 3 dimensions? Plus, minus? Yes, that is correct. We have each dimension for each flower, and this is a probability from 0 to 100. This is correct very nicely. I like that you not only type in plus, but even explain it a little bit. That maybe some other people also can then benefit from those small explanations. So that's great. So now maybe hopefully when looking at how it works, maybe then you would get it much better. So then if you have E by J, so that is the trace line in the matrix. So the trace line in the matrix contains the Jacobian, and here we have the Aij, and this will contain the same equation as on the Jamboard. So if you think about what we have here, there's a batch size, so and the A itself, this shape, A shape, is the batch. By the way, if you type in minus, that's valuable, but even more valuable would be if you type in some question of what exactly is not clear. So then this is this is taking all of the samples from batches and now looking only at the eyes, so like that, and then we would multiply it, because in this case this is a pairwise multiplication. This is not the dot product, because there are no extra dimensions inside there. This is just a pairwise multiplication. So 1 minus O of J, or not O but A. So else, so this is the middle, like this identity kind of line in the matrix. So identity part of matrix, or the trace. So if you look at the slide, that part of the equation is always there. So, and every other part of the matrix contains a different equation. So the different equation is EJ, and this is then minus A of I multiplied by A of J. Hopefully I did not mess it up. So far so good. And then we do the so then we do the dot product, matmul of J, with the chain rule. So here we apply the chain rule. So chain rule, and as we did yesterday with all of our equations, we just use the chain rule of the previous layer, and here, because we are multiplying with the matrix, we need to transpose the vector, and in this case the way how I will do this is by adding extra dimension. So self output grad, I'm not sure if I could do this without adding the extra dimension. Like if I would write it on the paper, like just by hand, I could do it without extra dimension, but here I need it. And then afterwards, so maybe I can even rewrite out what is step by step inside here. So the J shape is the batch, comma 3, 3, comma 3. Then the output grad shape is the, if I'm correct, it's 3. And then in order to do the dot product properly, I need to have this extra dimension at the end, so it doesn't change the data. As we talked many times, like adding the dimensions do not change the data. We can, so if it's not clear, then think about it like, for example, if you have some data inside like this 1, 2, 3, right? And if I rewrite it by adding extra dimension like this, it does not change the data. It's just adding the dimension, and the dimension is 1, and so it's not changing anything. So it's just changing the shape. So this is how it looks like then, and afterwards the grad shape is, I could be not nice and ask you to say it. Probably some of you could say it, but it is then the 3,1, because this is the same as with this biased stuff that we already talked. But the only problem is that this is not in the shape of like just a vector, so I want to remove that extra dimension, B3, something like that. So, and to remove that extra dimension, I can use the squeeze. Again, if I would use the for loop and then use the np dot, the dot product, I could skip all of this stuff. It would still work without these extra dimensions. But in this case, if I want to write it in one line, I need to add those extra dimensions as I did before. So anyways, this was explanation, and now I will like delete some part of it, and so that I can post the softmax to the Jamboard. And I really hope that I did not mess it up, because as you see, this is not that trivial. So I will probably not let you in the homework, like for the homework, the other parts of this code. Just don't want to make your life too difficult, but at the same time, this is kind of important. So then let's go to the cross entropy part. The cross entropy part is also not that difficult. This is much easier than the softmax, because there is no Jacobian matrix. So here, let's see, what we actually need. So we need y prime and y. So y prime, let's store y prime, and also let's store y. By the way, I added to the Jamboard this code of the softmax, so make sure that it's good for you. Maybe I did some bugs, so let me know. You already helped me today multiple times. I forgot to give cookie, but next time I will. So then here we have the average value, mean. By the way, also, if you think about the mean and sum, like right now in the optimizer, we're using mean there, but it could be also sum. So, and also here it could be sum. It's just the scalar then. So then we would need a lot smaller learning rate. So with the mean, it's easier. So here also it will be batch independent with mean. So np log of y prime value. This is really simple. You will need to implement the same loss function in the Pytorch yourself. You cannot use the implementation that is in the Pytorch itself. And if you use it, then you need to explain it. How exactly do you use it? Because, and I don't want you to use it. So self y prim grad. So there will be gradient. The gradient, the derivative is already given. I was so kind to give these derivatives for you already. Otherwise, sometimes I ask those students to calculate them, because it's actually not that difficult. So value except the softmax one is not nice. So okay, this one. Okay, good. Hopefully this is fine. We'll see that just in a second. If this is not okay, then we will see it spectacularly. So I'm adding the loss function to the Jamboard. Well, it's not added. Okay, now maybe I should add it in a separate slide. Let me see. No, it's fine. I can add it here as well. Okay, cool. So the loss function and the softmax is added to the Jamboard. Then the next part is we need to modify our model. So one thing, of course, that we need to do is add softmax at the end, layer softmax. But for the sake of the fun and understanding of what we're doing, I will not show you how to modify this model further. So finish modification yourself. But what I do, I will now hide this part from you, because again this is just a 10-second job. This is not something like mathematically genius that you need to do now. So this is just understanding of what you're doing, and if you don't understand, then you need to debug it and think about it. So here I'm adding this part, so you need to finish modifications yourself, and you need to add the softmax layer at the end, of course, to have the probability distributions. Meanwhile, I will do those modifications myself in my code and not show you. Then I will scroll down to the later part of the code and see it back here. So in this part of the code, I don't think we need to change much here. So the one thing that only needed is to calculate the accuracy. And if you look up here, I already made the code for you. I was so kind to make the code for you that it converts the indexes to the probability distributions. Normally, no dataset comes with the probability distributions, because that is not like it would be waste of the memory, because then you need to store all of the zeros for all of the other classes. It's much easier to just store the class index, and also you can bypass in many cases these probability distributions. But so that you have it here, it's already given for you. And I think if we just run the code, it might work. So let's see. Okay, this is not the correct code. Sorry, I was not running the correct code. Let's run it again. Close all plots. Okay, okay, it works. So the fun thing is that the accuracy only do not show any improvement, because the accuracy is not calculated. And I will leave this as a homework, because the calculation of accuracy, if you have two probability distributions, and if you add here a breakpoint in this line, then you should be able to understand how to calculate accuracy for this batch. This is really simple. Like if you think about it, like if you have two vectors of probabilities, right? So this item is what you have here. If you think about it, is that, let's say, item in this vector means that this is 100, let's say 90% that this is this class, 10 to that, 0 that, this would be actually y prime, because the y would never be like that. Then the y would be 100, 0, 0. And this, in this case, we can look at the highest prediction of the probability, and this would be this case, and we would assume that this sample is correct sample, and this is accurate sample. But in the case, if this would be 10% and 90%, that means that this sample is not correct, so this is a 0% accuracy. So you can do that yourself. There will be, let's say, actually it will look like something like this, the 90%, 100%, 10%, something like that. So you need to do that accuracy yourself. I will add that condition to the homework as well, because I think I did not was specifically listed that one. Hopefully I did. But the loss function then reduces, and the code itself is correct. So this part is great. Let's see who gets the highest accuracy for predicting the correct class of the flowers. And then for the homework, I will also give you to implement the same exact code in Pytorch. So that will be your homework as well. So right now, let's do, so we have, let's say 5 minutes left. So maybe you have some questions so that you would be able to fill your homework. So if you have any questions right now, please write in the chat. And if no questions, then I will just prepare the homeworks and you finish this code. And next time we'll work on a little bit on the image classification, on the like we will have images and the convolutions, and then we need to build the models that can classify, is this image, for example, a dog or cat or something like that. And again, we will work with equations, and we will do this by hand, and we will understand what we do. So that will be quite fun, hopefully. So if you have any questions, let me know in the chat now, or speak no more. And then let's see next week who gets the highest score in the course. And yeah, if you have any other comments, questions, then write to my email. So that's about it for today. So I wait for a few minutes for some questions, and then we'll wrap up. Okay, so Kristaps, I have a question up here. I think I answered the question. So yes, each dimension is for each flower, but then the other question that not understanding what's going on is that the loss function is reducing, and we are predicting the correct class from the inputs. I don't know, so these models are these are machine learning models. They are trying to predict from the inputs some outputs that can be used later in some samples that were never seen in the training set. And this is all done with all of these mathematical operations that we covered. So I really don't know how to help much in that direction. Only I can, of course, share you some other courses and materials. I will definitely do that. I will add to preparation materials for the next session some of the materials in the deep learning that I know are really good, and let me know then if that helps. But if it's not helping you, then you can try to write me an email, and if you write me an email and we set up a Zoom call, maybe we can resolve some I'm not understanding what's happening. I hope that at least other people are understanding so far, because it will get even more difficult very soon, and it's already quite inside the machine learning. So yeah, that's it for today. Okay, I see another question. Are we supposed to build the graph in the Jamboard's 5th slide? So the 5th slide, thank you for some question that is actionable now. So the 5th slide, no. So the 5th slide is just an illustration. You need to build your 8th slide. So use fix code in 8th slide, and add accuracy, and then re-implement whole stuff in Pytorch. And I will add another task as a homework task, where you would use the another template and just build up the whole stuff in Pytorch. As you imagine, in Pytorch it will be much easier, but first please do this in the Numpy. I already gave you a lot of variables, so those variables that I gave you are the key ones, and right now, like basically if you can finish my Numpy template, then there will be absolutely no problems for you to finish Pytorch template. So that's it for today. So I guess all of you now understand what the deep learning is all about, and hopefully you can start loving it, and it will be really a powerful thing that we can use later. So no, you don't need to completely change the model, just fix the some of the parameters. So I will add that